Hi folks, welcome to the last part of this lesson. So we're going to take a look at the last question on the worksheet. So it says find the vector, parametric, and symmetric equations of the line that passes through this given point and is perpendicular to both of these lines. All right, so a little more complicated than the other ones that we've seen. So I'm going to draw myself a diagram again. Make no effort to be exact here. So let's say I've got two lines in 3D. Okay. And what I'm looking for is I'm looking for a third line, which is perpendicular to both lines. Okay, so it's perpendicular to this one here, but it's also perpendicular to that line. So I've drawn it to try to give a sense of perspective here. So let's remember what we need to find these equations of a line. Well, we need a point, which we already have. So there's our R naught. All right. And the other thing we need is a direction vector. So a vector that's in the direction of this line here. Okay, so this is where I hope you thought of something that we've seen before, because we have these two lines and we know that the vector that we're looking for has to be perpendicular to both of these two lines. If it's parallel to the line I'm looking for, it must be perpendicular to these two lines. And we've seen that before. We've seen that with the cross product. Okay, however, you can't take the cross product of two lines, but what you can do is you can take the cross product of the two direction vectors of these lines. So if we try to use a different color here, if we take these vectors, remember we can place them anywhere. If I take this direction vector and that direction vector, okay, and I take the cross product, I'm going to get a vector that's perpendicular to both. In other words, a vector that's going to be parallel to the line that I'm looking for. All right, so in order to find this direction vector, I'm going to take the cross product. All right, so let's do that down here. So what are our direction vectors? So these are both given in symmetric form. So to find the direction vectors, I just have to look at the denominators. So I've got -4, -6, 3, and then here we have 3, 2, 4, 3, 2, 4. Okay, and so I'm going to bring over this -4 and 3, and let's calculate this direction vector. Okay, so remember, start without the x's. So we have -24. So remember, I'm multiplying and then I'm subtracting that product. So -24 minus 6 is -30. All right. So here, now let's go for the y component. So here we have 9 minus -16. Okay, so 9 minus -16 is 9 plus 16. So what is that? That's going to give us 25. Okay. And then here we have -8. Again, minus -18. So -8 plus 18 is just going to give us 10. All right. So here's our direction vector. But remember, I can use any vector that's parallel to this line. And I see that I can get a much nicer vector parallel to the line. So I'll call this M1. What I'm going to use as my vector parallel to the line that I'm looking for is, well, I'm going to take a scalar multiple of this. I'm just going to divide this by 5 to make it -6, 5, 2. So remember, I can use any vector parallel to the line, so I might as well use the simplest one possible. Okay, so now that I've got my point and I've got my direction vector, I can write out the three equations. So let's start with the vector equation. So we have R naught, so R is equal to R naught, which is -6, 4, 2, plus any scalar multiple of my direction vector. So that's -6, 5, 2. Okay, with t being any possible real number. Okay, let's switch that out now to parametric form. So we have x is equal to -6 minus 6t. Okay, for y we have 4 plus 5t. And then for z we've got 2 plus 2t. Okay, and again, t can be any real number. And lastly, let's put it in symmetric form. So x minus the x component, so x minus -6, x plus 6 over -6 is equal to y minus 4 over 5 equal to z minus 2 over 2. Okay, and there's my symmetric form. Okay, so this is one of these tricks that I want you to keep in mind, that if I'm looking for a line which is perpendicular to two given lines, then I should be thinking about using the cross product in order to find my direction vector. And remember that if I'm looking for a direction vector, it could be any vector in the same direction of the line. So if I can make it simpler by dividing out a common factor of all three components, good thing to do that. Okay, that's it for this one.